Hello, welcome to the course SJPHY2C02 Optics, Laser and Electronics. The contents of today's lecture is taken from Principles of Electronics by V.K. Mehta. We will continue to discuss topics from Module 4, Electronics. In the last couple of classes, we discussed about the working of a rectifier, which essentially converts AC voltage into DC. Here, the output DC voltage depends on the input AC voltage. When the input increases, output increases. Similarly, when input decreases, the output is also going to decrease. So if you are looking at some applications where you require a constant DC voltage, then the rectifier alone cannot do this job. So for that, you need to use a voltage stabilizer. So here what happens, the output of the voltage stabilizer is going to remain constant irrespective of the changes in the input voltage or the load resistance. Now, one of the ways in which you can design a voltage stabilizer is by using a special type of diode known as a Zener diode. Zener diode is a properly doped semiconductor diode. By the way, semiconductor diode is also known as a crystal diode. So with a sharp breakdown voltage. So we know the general working of a diode or the typical VI characteristic of a diode, right? So here during the forward bias, you can see up to the point where the biasing voltage exceeds the barrier potential, you do not have much current flow, but once the barrier potential is crossed, you have a considerable increase in current along with the increase in the biasing voltage. So this is the forward bias, and in the reverse bias, initially there is not much current. In the case of ideal diode, actually there is no current, but if you take any practical diode, there is a minor amount of current, a weak amount of current due to the minority carriers. But once it reaches a particular point known as the knee voltage, now if you increase the bias voltage further, then you have a drastic increase in current. So here what happens, so this is because the diode is entering the breakdown region. So we have discussed this avalanche effect. So you have a large increase in the number of minority carriers at the PN junction, and because of this minority carrier, you have a huge increase in the current. So this is the breakdown region. So the breakdown of the PN junction was first explained by the American physicist Clarence Zener. So breakdown voltage is also known as Zener voltage Vz. And the sudden increase in current is called Zener current Iz. Now, value of the Zener voltage depends on the amount of doping. If the diode is heavily doped, depletion layer will be thin and the breakdown happens at a lower reverse voltage. In other words, Vz will be lower. Whereas for a lightly doped diode, Vz will be higher. When forward bias, a Zener diode behaves exactly like a normal diode. But for a Zener action, basically you need to drive the diode into the breakdown region. In other words, for Zener action, you need the Zener diode to be reverse biased. So mainly you use Zener diode for voltage stabilization applications. So whenever you use a Zener diode, typically it is reverse biased. Now, some of you may be thinking that when a diode is operated in the breakdown region, is it not going to damage the diode, right? This is what we have discussed in the case of a normal diode, right? Because you have a huge current across the PN junction. Whenever there is current flow, there is a power dissipation due to Joule's heating. In other words, a huge amount of heat is generated at the PN junction, which is eventually going to damage the diode, right? But one thing you have to remember, you are not going to use a Zener diode alone. because the main application is voltage stabilization. So the output of the Zener diode is going to be given to a load or another circuit, right? If you look at your household, typically you connect a voltage stabilizer to a refrigerator or a TV, right? So you have a load circuit here. So a Zener diode is not going to immediately burn just because it has entered the breakdown region. As long as the external circuit connected to the diode limits the diode current below the burnout value, the diode will be safe. So you have to choose your circuit resistance in such a way that the Zener diode is not burned even though you are operating all the time in the breakdown region. So this is the typical symbol of a Zener diode. This is the P side, this is the N side, and this is the actual picture of the Zener diode. How do you identify P and N? The N side has a black mark. Now, Zener diode who works in two states. One is the on state and second one is the off state. So what happens during on state? When the reverse bias voltage is greater than the breakdown voltage, so essentially if you look at this VI characteristic figure, we are talking about this breakdown region, the reverse bias voltage greater than the Zener voltage or the knee voltage. So here you can see that in this region, the current increases drastically, but the voltage is essentially constant. Right? Voltage is the x-axis, so this point is almost a constant. On the y-axis you have a large change in current. So the voltage across the diode is constant when the reverse bias voltage is greater than the breakdown voltage. So in the breakdown region, for an ideal Zener diode, ideal means zero internal resistance, the voltage across the diode is going to be constant at Vz. So you can represent the Zener diode by a battery of constant voltage Vz. What does the battery do? It will give you a constant voltage. So in this region, in the on state, your diode, the Zener diode, also going to have a constant voltage across it. Okay, so on state means the Zener diode working like a battery, right? So as long as the reverse bias voltage V greater than Vz, then for all practical purpose you can treat it as a battery of constant voltage. Off state means when the reverse bias voltage is less than Vz but greater than 0. So essentially you are talking about this region, greater than 0, less than Vz. So we know that this current is very small, current due to minority carrier. So for all practical purposes you can say that the diode doesn't conduct, right? Or if you are considering an ideal Zener diode, then the reverse current is 0. So you can represent the Zener diode in the off state by an open circuit. Open circuit means there is no current, right? So if V is greater than Vz, the Zener diode is in on state. It works like a battery of constant voltage. If V is less than Vz but greater than 0, then the Zener diode operates in the off state where it is as good as an open circuit. Now, how does it act as a voltage stabilizer? So this is the circuit diagram of a voltage stabilizer. So you have output of the rectifier coming here, then this is the load resistance RL across which you need to take the output voltage, and the Zener diode is connected in parallel to the load resistor, and the diode is always reverse biased, and you also have a series resistance R to limit the current in the circuit. So the reverse bias Zener diode is connected in parallel to the load, and you can see that the input voltage here is EI, and the output voltage or the voltage across the load resistance is E0, and Vz is the Zener voltage, and IZ is the current through the Zener diode, and IL is the current through the load resistor IL. And if you look at this circuit, you can see that the Zener diode and the load resistor, these two are parallel. So typically, when two components are parallel, the voltage drop across both of these is going to be the same. And if you look at the current flow starts from the positive terminal and ends at the negative terminal. So current comes from this point. When it reaches here, it gets divided into two. One is through the Zener diode IZ and another one is through the load IL. And at this point, these two currents combine together. So the total current in the circuit I, or the current which flows through the resistance R, is nothing but IZ plus IL. Now, as long as the input voltage EI is greater than the Zener voltage VZ, so remember these are parallel connections, so the same voltage is going to drop across this particular point. So if the reverse bias voltage EI is greater than VZ, then we know that the output across the diode is going to be constant at VZ. Since RL is parallel to the Zener diode, the same voltage is going to drop across RL2. So as long as EI is greater than VZ, the output voltage E0 is constant at VZ. And the beauty of this circuit is that the output voltage E0 can remain a constant over a wide range of EI and RL. In other words, the changes in the input voltage or the load resistance is not going to affect the output voltage. I will explain that shortly. What's the purpose of this series resistance R? This resistance is going to absorb the output voltage fluctuations so that the output across the load remains constant. Now let's see how this stabilizer circuit is able to withstand the changes in input voltage and the load resistance. Suppose input voltage EI increases. So ideally, when the voltage increases, the output is going to increase, right? Since the Zener diode is in the breakdown region, we know that it is equivalent to a battery of constant voltage VZ, right? So since this voltage is constant, RL is parallel to this battery. So whatever is the voltage here, same thing is going to be dropped across R. So as long as VZ is constant, the output across the load resistance is also going to be constant at VZ. But the circuit has to respond to the increase in input voltage, right? So here the role of the series resistance come into picture. So the excess voltage is dropped across the series resistance R. So when the voltage increases, the total current in the circuit is going to increase. So I is going to increase. Now, where does this increase come from? We know that I is IL plus IZ, and the voltage across RL is constant, which means IL is going to be constant. So the increase in current should come from an increase in IZ. In other words, the Zener will conduct this excess current so that the load current remains a constant. So even though the total current in the circuit increases when the input voltage increases, the load current is the Zener current is going to increase accordingly so that the load current remains a constant, thereby the output voltage across the load is going to remain a constant. Now, what happens when the the load resistance changes. So suppose that the input voltage is constant but the load resistance RL decreases. So ideally what should happen? We know that the output voltage is nothing but the load current multiplied by load resistance. So when load resistance decreases, ideally this output voltage should decrease. But here this is what going to happen when this resistance value decreases, the load current is going to increase. Now how does this increase? We know that the total current is IZ plus IL. So when the load resistance decreases, the Zener current IZ is going to decrease. So whatever value decreases here, that is going to add to the load current. So you have IL plus RL remaining constant once again. So in summary, when the input voltage EI increases, the Zener current IZ increases proportionally so that the output voltage is going to remain constant. Similarly, when the load resistance RL decreases, in response the Zener current IZ is going to decrease so that the output voltage once again is going to remain a constant. So this is how the Zener diode is able to provide a constant voltage across the load resistance irrespective of the changes in the input voltage and the load resistance. Now what is the voltage drop across the resistor? So we know that these two components, the diode and the load resistor, are in parallel, and this parallel combination is in series with the load, with the series resistance R. And this voltage drop across the diode is Vz. So the same voltage is going to drop across RL. So Vz is going to drop across this parallel connection, and the remaining voltage is going to drop across the series resistance R. So the voltage drop across R is going to be EI minus Vz, or EI minus E0. And current through the resistance R, this is nothing but the load current IL plus the Zener current IZ. So I can write I equal to IZ plus IL. So how do you find the value of the series resistance R? From Ohm's law we know that resistance is voltage by current. So this is EI minus E0 divided by IZ plus IL. So this is how you choose the value, the required value of the series resistance in your stabilizer circuit. So that's about the discussion on diodes. So before winding up, I want to tell you one important point. Especially when you are doing your practical experiments in your laboratory, you need to keep in mind that all the crystal diodes are extremely heat sensitive. Even a small increase in temperature is going to result in a large increase in the current. Now every diode has what is known as a temperature rating. This is the maximum temperature it can withstand. So if the temperature exceeds the temperature rating of the diode, then the increased flow of the current is going to produce large amount of heat, which eventually damages the PN junction. Therefore, one must be extremely careful while soldering the leads of the diode. So typically, you construct your circuit on a board. There are two types of board. One is the breadboard and another one is the printed circuit board, or PCB. So in breadboard, you do not have to solder the electronic components because all these holes are internally wired. If you look at the two sides of the breadboard, these are horizontally connected, all these holes, and when it comes to the center part, all these holes are vertically connected, so you do not have to solder the components. You simply insert the component, and you insert the diode, you insert the wire, and the wiring and the connection is internally done. So usually you use for small experiment this kind of breadboard, but if you take any electrical appliances like a mobile phone or an LED bulb, they mainly use a PCB, because here in a tiny space you can accommodate more number of components, whereas in the case of breadboard it is inherently bulky. Okay, so when you use a PCB, you need to give connection using by soldering the electronic components. So you use a soldering iron which is heated to a particular temperature, then you use that to melt lead, which is a conductor, and using the molten lead you make the connections on the back side of the PCB. So when you're soldering a diode, you need to be very careful, because if you touch the hot soldering iron to the legs of the diode for a longer time, then that's going to increase the temperature at the PN junction, and which will eventually damage the diode. Okay, so this you need to keep in mind when you do your lab experiments. So that's about the theory of diode. Before winding up, let's do a quick problem. For the circuit shown in this figure, what is the output voltage, the voltage drop across the series resistance, and the current through the Zener diode. So you have 120 volts from a rectifier or something, and the Zener voltage is 50 volts, the load resistance is 10 kilo ohms, and the series resistance is 5 kilo ohm. Now, first thing we need to find in what state the Zener diode is operating, the on state or the off state. So you remove the Zener diode and calculate what is the open circuit voltage, the voltage between these 2 points. Okay, so when you remove the Zener diode, you have only 2 resistances R and RL connected in series to the power supply of 120 volt. Okay, so what is the current in the circuit? Current is total voltage EI divided by the total resistance R plus RL. Now, what is the open circuit voltage? Open circuit voltage is a voltage between these 2 points, which is also the voltage across the load resistor, right? So once you know the current, how do you find out the voltage drop? Current multiplied by resistance is the voltage, right? So EI divided by R plus RL, the current, multiplied by resistance RL will give you the open circuit voltage. So this is 10 into 120 divided by 5 plus 10, which is 80 volts. So 80 volt is going to be the voltage that is getting applied across the to the Zener diode. Okay. So this is the reverse bias voltage. So 80 is greater than the Zener voltage 50 volt. So since the reverse bias voltage is greater than the Zener voltage, the diode is going to be in the on state, right? So we know that in the on state, a diode can be represented by a battery of 50 volts. So you can replace the Zener diode with a battery of 50 volts. So this is the equivalent circuit. Now let's do our calculation. First thing, what is the output voltage? Whatever is the voltage across the Zener diode, same is going to be the output voltage, because the load resistor is connected in parallel to the Zener diode. So 50 volt is going to be the output across the load resistor. Now, what is the voltage drop across the series resistance? So we know that total we have 120 volts. These 2 components are connected in parallel, which means their voltage drop is going to be same. So 50 volt is going to be dropped across these 2 components, and whatever is the remaining voltage, that is going to be dropped across the series resistor, right? So 50 dropped here, so 120 minus 50, the 70 is going to be dropped across the series resistance. So And final one, what is the current through the Zener diode? Okay. So we know that the 50 volt is the voltage drop across the load resistor. So let's calculate what is the load current. Current is voltage divided by resistance. So 50 divided by 10 kilo ohm. So 5 milliampere is the load current. And what is the current through the series resistance? We know that 70 volt is dropped across this resistor. So corresponding current is 70 volt divided by 5 kilo ohm, which is 14 milliampere. And we know that the total current I is nothing but load current IL plus Zener current IZ. So from this I can write IZ equal to I minus IL, which is 14 milliampere minus 5 milliampere, which is 9 milliampere. So that's about the theory and working of diodes. In the next class, we will discuss about the working of transistors. So in diode, as we know, we have only one p-n junction, but in transistor, we are going to have two p-n junctions. So that's for today. Thank you.